confirm that the screen sharing works. Can you see it well? Let me just confirm that, please. Okay, good.
You're good.
Thank you for hosting me here. I really wanted to be in Golden, meet with all of you. I used to actually live pretty close to Golden about 12 years ago. So this is a nice afternoon. Thank you all for hosting me here. What I'll be talking about is the resource estimation and what are the risks and opportunities associated with it, and why we should be talking about it. Generally, this topic I've covered like few hour sessions to few day sessions, actually a couple day sessions. I'll try my best to really cover enough topics so that we have good interaction at the end. I think that's the fun part. Thanks, Fati, for introducing me. This is my one slide introduction I always carry with me, just to highlight what I have been doing over the last, close to 25 years now. I've been to many parts of the world, but most of my projects are actually from nearly about 29, 30 countries. I was just counting the other day. It's roughly about 100, 120 projects I've done. Various reviews and complete projects and mining projects type of things. I have covered a lot of commodities, except you see that the coal is not listed there, and lithium I don't list that. There are only few projects I've done in coal and lithium, but I was lucky to have done actually projects in diamond. Then also, some of the commodities that you luckily get to, get your hands dirty. So I feel good about that. Yes, while I was in Denver, I was working for Pincock, Allen and Holt, and it's in Sim Street. You know where it is, pretty close to where you are. I also work as a CP or QP, depending on where we are. I use two affiliations for that, CPG from AIPG or registered member of SME. I'm also associated with a bunch of societies, mainly SME, GSA, and SEG. And also, I contribute to a little bit of to the academic world, being in the editorial boards of a couple of scientific journals. That slide is to say that, I'll be showing you some diagrams, some numbers today. Those are modified numbers, but based on the real projects. Please don't quote them. I know that it's being recorded, and I'm not giving you any professional consulting today. So, but that doesn't necessarily mean that I will not be answering questions. We'll be actually having a Q&A session at the end. Please, I'll be showing some also diagrams really with an intention that you ask me questions. Okay. Before we go to even the risk associated with the resource estimates, we should understand what the resource estimation process is. To me, it is a 7-step process. Goes really step 1 to step 7. Sometimes actually we stop at step 6 in here, like here, and we start with the data. We collect the data, interpret it. They'll spend a lot of time on what I call it EDA, exploratory data analysis. Then, as we know, many people, we spend a lot of time in estimating grades, let it be gold or copper or iron ore or whatever that commodity may be. Classification, resource classification, I'll touch on that a little bit. Model validation, I personally spend a lot of time on that, whichever work I'm doing. Resource reporting, that's very specific to some requirements. Sometimes it requires reporting resources, sometimes it's not. But at least 6 steps are there. Those lines, those arrows shows that sometimes you have to go back and forth between 2 steps. For example, we were doing the resource classification, then we also, doing the model validation, we said, well, how do we learn from there? Do I need to go back and reclassify the resources in one portion of the project? That always happens. The takeaway from this slide is resource estimation process is an iterative process. It's not that you just do it once, it's done. It's not like that. So it is an iterative process, and it is a very stepwise process. In my professional, training programs, I spend pretty much 40 hours going over all 6 steps. And most of the time we spend on these 4 steps. EDA, a lot of statistics we do, grade estimation, a heavily computerized process. Resource classification requires a lot of understanding about, continuity, geology, and what the quality of the estimates that we do. A lot of things in there. It's not very straightforward process, resource classification. And going back and say, hey, did we do it well? So these 4 steps we spend most of the time. Okay, just before we go into resources, this is how the terminology is used today. The mineral resource is basically, it's a solid material. Of course, I understand there's lithium also included today, but it is a material of economic interest. In this diagram that you are seeing, this is a worldwide or internationally accepted diagram. I believe I borrowed it from Crisco 2013 template, but Crisco 2019 template is also available. I encourage you guys to go to website of crisco.com and download that 2019 template. It looks different, but material-wise, it's pretty similar. This diagram is very important when we're referring to resource or reserve. Like I said, resource is really the concentration of the occurrence of material of economic interest. Now, it has 3 classifications: inferred, indicated, and measured. Then if you want to take portion of the resources into reserve, only indicated and measured resources can be converted into reserve. And what is reserve? Reserve is the economically mineable part of the MNI, that the measured and indicated resources. So inferred resources, they cannot be combined with measured and indicated for that purpose. So indicated and measured resources, they are candidates for becoming reserves. Inferred resources not. If you have more questions, I can spend towards the end. Now, grade tonnage curve, like I'm assuming that you guys all know. If not, this is just just a review type of thing. It's a typical grade tonnage curve, right? At any cutoff grade, if that red arrow shows the cutoff grade in the x-axis for any commodity, and the blue line is the tonnage line, and as the cutoff grade increases, the grade of the material that is represented by this blue line also increases, but the tonnage decreases, right? In any mine, higher grade material are less and less. So that's the grade tonnage curve. That's how we read it, right? On the one axis, tonnage axis, we read the tonnage, and the grade axis, we read the grade. Now the point is, okay, we can combine these 2 lines into one line that is metals, right? At any cutoff grade, you can see the metals can be calculated. I'll show you an example of how it is done. Now, like I said, inferred resources cannot be combined with indicated or measured resources. This is just an example. Like I just made up this table in here. Let's say it's a cluster tree open pit mine, okay, whatever that mine is. This is how it is reported. The indicated resource line is there, and it is actually the input resources line is separate from indicated. If this table had measured resources, it can be combined with indicated, or can be actually stated also separately. It's very important at these 8 points, particular to this table. In this instance, this project decided to put these 8 qualifying statements. One of the important one is the cutoff grade. At what cutoff grade is grade and tonnage are being reported to the public or in that particular report. Then there are a bunch of other information are also provided. In this particular case, to meet certain criteria as described by the guideline that we used or that was used for this this table, there was an finan-cial was developed, and these are the technical information that is also provided. See, it is very particular about what is resource and what is reserve. So the point is, these technical terms should not be used loosely at all. The estimates are grades and tonnages above cutoff grades. Now, the info resources are reported separately. It's just an example. One other thing you should actually notice, what we are actually reporting here, we're only reporting one number, right? So we're reporting only one number, that is tonnage in here. Sorry. So the tons and the grades, as if this is static. Okay, as if the deposit, you can just go and get that amount of material. Okay, just keep that in mind as you progress. But I'm using another term in here, uncertainty. By that, what I mean is, well, let's see this is a cube where we are trying to estimate the grade using various techniques. Maybe 1.7 GPT comes per ton. One set of criteria, so well, it's actually 1.7 GPT. On another criteria, set of criteria, could actually estimate that. Another one, estimate that. It can have various numbers. You see, it doesn't say like in 2.5, it's very close numbers, but it's not one static number. Okay. So the two terms, one is an estimate, it's not a calculated number. So it's not one single number, it's an estimate. That is the best possible approximation of the grade in that particular block. Block is nothing but a two-dimensional space. That really means that we really don't know what the exact grade gonna be. When you say we don't know, that all other possibilities then open up. That is uncertainty. It's uncertain that we know what the exact grade gonna be. Okay, just keep that in mind. Just uncertainty. We're not going to risk yet. So what I'm saying is, the grades may vary. There may be actually, it may be what this number or that number. That all depends on various criteria. Again, this list is entirely based on my own experience. And is it geology? How simple or what type of mineralogy is in there? Quality of quality of the samples. How the geology data was put together. How close the sampling was. How the grade estimation was done. I know that I'm talking to the CSM graduates, you are students there, you may have access to a number of other software tools. It doesn't matter what software you use. Okay, we'll be doing, when we do the grade estimation, we'll be kriging, simulation, all different things. But it all depends on the technique and parameter that we use. I'll come to some of the examples. The last one is probably least discussed, is the density. How well you understand the density of the rock where the content material is being estimated. Example, geology. On the left-hand side, this is a granite hosted, it's a copper deposit. Again, it's from South America. See, these are two rock types I'm identifying. Rock 1 has a lower grade concentration, and rock 2, that this group of people told me that it is better grade, but less volume. Again, on the right-hand side, that's also copper deposit. It's a vein controlled, and it's a structurally controlled and vein host, vein type copper deposit, very dense kind of vein system in here from Brazil. There are many geological factors are there, but the two that are very important. One, the style of mineralization, whether it's massive or vent type or what kind of mineralization is this? The sedimentary rock, is a gneiss hosted rock, or is a porphyry massive or what? And the controls of mineralization, that is a lithology controlled or structurally controlled, or is alteration, hydrothermal alteration, or whatever it is. These two are very important. I also said the type of the quality of the data and the spatial density of the data can also change the estimation. Here on the left-hand side, you see an example of, it's a very simple example. I always check when I see the gold and silver data. If it is ppm or grams per ton. In this particular case, what I found, I said, well, this is the typical thing, it's a simple, actually, just a scatter plot. Actually. But I said, well, what the conversion factor you guys used? Well, we used 34.1917 something. That's rounded up to 34.2. When I plotted them, as you can see, the low grade stuff in here, they are not 34.2. Just be careful. They will impact the quality of the estimation. Right-hand side, what you see on the top right-hand side diagram, you see the drill holes there. The pattern of the holes is totally different from the pattern of the holes in the right-hand side bottom diagram there. The upper one is the copper deposit from South America. The lower one is a lead zinc deposit from US. Totally different type of drilling. Spacings are different. It depends on the complications in the geology and also many other criteria. All that will impact the quality of the estimation. This is a fantastic paper by June 1. You can actually get this paper downloaded from the website. Actually, June is a fantastic paper. But it shows that when you take the drill hole data, you can actually see this, the yellow yellow diagram over there. They represent the hand-drawn interpretation of the geology. In this case, it's really not a geology, the grade shells from the exactly same drill hole data. And then they put that data into an automated one, and on the right-hand side diagram shows the how the computer has generated it. And what you can see, I compared actually the similar features, similar things actually similarly done geological models in different deposits. They can be actually, depending on how the computer has generated the models, they can be very different in volumetrics. So is one interpretation better than the other one? Don't know. You got to test it, right? On this diagram from the same paper, it shows that you use the exact same drill hole data, just changing the parameters. It will tell you, probably computer is going to give you the results that will look like two different deposits. So parameters are important. Okay, so that would actually change the volumetrics of the estimation. That is a caution. I always do that in an industry. Something quick and fast looks nice, shiny, doesn't necessarily mean that it's correct. Okay, it's always please validate the model to do that. Okay, here's a real example. Of course, the diagram, the numbers have been actually, I have to change the numbers. So what is the impact of all that? So I took a gold data and just ran some models on it for this presentation. I said, well, I take up the old model is this orange one. Look at the grade line for the exact same tonnage line. The grade line is different for new model and old model. So the old model shows a different grade profile, and the new model shows a different grade profile. If I convert that into metal quantity, you see the, again, new model shows the much higher metal at different grades. I'm going back one step. If that is the cutoff grade, you can see that we're predicting two different types, two different amounts of metal in this particular case, just changing the two different types of interpretation of the geology. The rest remains constant. So just introduces you in the real life how geological interpretation can impact the grade and tonnage estimates in any deposit. Estimation parameter, that's a very big subject, and try to put together, put everything in a couple of slides. One big topic which is discussed is source ellipse, the size, shape, what kind of source ellipse, and how much data it can take. Imagine that these dots represent the drill hole composite data, and we trying to estimate the value of this block. Depending on the source ellipse, let's say that the pretty large source ellipse, you can use all the data, right? Maybe a smaller source ellipse, maybe an isotropic kind of ellipsoidal source ellipse. It can actually exclude some of the data in here. Maybe the source ellipse goes that way. So depending on the source ellipses, the estimation can change too. Okay, again, I'm showing the same diagrams, some numbers or similar numbers. You change the source ellipse, you'll see, and go and check any block. You'll see every time you change the source ellipse, there's a possibility that the grade is estimated differently for any block. Here's another real example. I'm showing the tonnage line. The yellow line using a spherical source ellipse. Everything else remaining constant. This red line is using an elliptical source ellipse. There's about 40% difference in tonnage, just changing that source ellipse. When I said, okay, well, you guys have a lot of high-grade stuff in here. Okay, that's a whole different analysis I do. Let's make the source ellipse very small when it hits certain high-grade value. This is a zinc silver type mantle deposits in Mexico. When I do that, this is about 75% difference in tonnage at that cutoff grade. I'm not disclosing the cutoff grade even in this diagram for good reason. But the point is just changing the source ellipse and make differences in the grade tonnage estimates. Techniques. I'm assuming that you have gone to the geostatistics course by Professor Kathy or someone else at CSM. This is my simplistic way of classifying the interpolation techniques. Non-geostatistical, we don't need a variogram in here. Geostatistical starts from kriging. It can be ordinary kriging or simple kriging, and there are families of those, and indicator kriging or MIK, and also families of conditional simulation. If I take this kriging to this side, these are all deterministic technique. So kriging is a deterministic technique, okay? Linear. These are all probabilistic techniques. If you have more questions, please stop me. I will have more time towards the end of this presentation. Just changing the interpolation technique in this particular example, it's a copper model. The model one, that is, just pay attention to this tonnage because on the grade line, there is almost no differences. The model one is the red, the green one, the ordinary kriging. Model two, model one is the blue one, the ordinary kriging. Model two is the green one, is using the inverse distance square interpolation technique. Just changing the techniques makes the differences in this particular case in the tonnages. Okay, in this particular case, I believe we are trying to get a 1.15 or something. There's a substantial differences in the tonnage. Why? That's another question. Why this? Just changing the technique, how can it make such a big differences? Simply because one of the main reasons was this is skarn type deposits where the distribution is not smooth. So you cannot really just use a linear technique and get good reliable estimates. So what we have learned so far, the grade tonnage estimates are not static numbers. They may change because of the nature of the geological complexity or interpolation related issues. An estimate is a part of a set of outcomes, like I showed you for one particular block. Some of the deposits I handle, they have hundreds of thousands of blocks in a model. So imagine that every block has a set of outcomes. An example, here is a cross section. This is a copper deposit actually. The hotter the color is better the grade. So let's say that only that way. The lines that we're seeing here are the drill hole intercepts, and the block colors, blocks are basically these, regular shape features in that cross section. Let's take that one block. So that block can be part of that grade tonnage curve, right? Like I said, this block can have many different possibilities. If you take them all, it can probably form a histogram of each and every block, right? So does that mean that you have to run a 200 different estimates? Some people used to do that actually, but just know at this time that a block has an estimate. So it's an approximation, but it has a range of possibilities. It can all fit into one histogram. If that's the case, what really that means, a grade estimate is only one of the many possible outcomes. That means it's distribution of grades. I'm just simplifying in this diagram, assuming that this is a normal Gaussian distribution. As we know, that doesn't exist. A pure Gaussian distribution doesn't exist in mining industry. But we assume that because of underlying theory. A deposit or a grade estimate can be above the mean. That means when that happens, we say, well, it's an optimistic case. When an estimate goes the mean of all the possibilities, you can call it it is a potential risky case, isn't it? What we're trying to do here, we're trying to simulate the values for any block. That's the beauty of that. You can actually simulate it. Okay. So it's important to know. It's important to know that the distribution of all possible outcomes so that we can actually quantify the uncertainty that is called risk. Risk is basically when you can quantify it, it's called risk. Okay, so it is when we have possibilities and you have a potential histogram, you can always quantify it and you can say, well, if it is risky or if there's an opportunity. To me, it's actually risk can be positive or negative. Okay, you go to different forums, they use different terminology. Again, the same grade tonnage curve, if I take it, like I said, this tonnage line may have an optimistic case, an upper case, or a lower case. That's a possibility. Same as tonnage line, so the grade line. What really that means? Now, which one was used in the mine planning then? Possibly that one, but that's that number. Like I was trying to explain in the last slide. So is this our mine plan is at close to mean? That's what we want to be. Mean of all potential outcomes, or is it on the left side? It can be actually a potential risky side, or maybe on the other side, it's maybe actually more positive side of. So if you have multiple scenarios, you can assess the risk and potentially also you can assess how much opportunity I have going forward. Let's look at some of the real examples. Here is something actually I miss Harry here, Dr. Harry Parker. This is a personal communication, and he shared that with us. He said, based on his own experience, about 45 years or 50 years in the industry, said a 10% error in the grade estimation can result in 30% difference in steady-state cash flow, and the NPV impact can be as much as 60%. And Harry, when he presented, we had a lot of slides in it, but that's kind of the point that we're trying to make here is try to be careful when you're doing the grade tonnage estimates, because we know that it's an estimate. We're trying to get as good as possible. So we're trying to, that's the meaning of basically getting a best estimates, knowing the fact that it can have, there's a potential for achieving less, or there's a potential for getting more when we go to mining. So it is important to get the GT estimates correct and understand the risks and opportunities associated with the estimated quantities. So the point is, again, understand the distribution of outcomes. what we do in the process in nutshell, you have the geological data, some videography is done, we do some estimation, or we do simulations of the estimates. That means you get a histogram of for each and every block that will look somewhat similar to the histogram that went into the model. If we do that, this becomes a simulation of the reality. Each and every realization has an equal probability of occurrence, and average of all realizations may represent the reality. Now, often I get a question: is the average of all the simulated realizations is going to be the same as the creek estimate? Depends. It's not always true. Conditional simulations are advanced geostatistical techniques. What you can simulate the grades. That most of the time I see we do. We can also simulate the grade, rock types, density variations. If you actually geomet type of variables like recovery, if you are lucky to get a good reliable data. In this diagram coming from a real project, of course, I've modified the number shown here. What I'm trying to show here is, sorry, this is an animation. In this case, this was a copper deposit. What I was given is a bunch of data, and the black line shows the grade line, and this is the tonnage line for the resource model. That's what is there. Using ordinary kriging as an estimation technique, this black line becomes a tonnage, grade line, and this purple line becomes the tonnage line for the resource model I was given. So we did a bunch of simulations. I think I ran about 200 simulations on this. So okay, fine. Let's go to the mean of all the simulations and compare that with this black line, keeping the tonnage line constant. Okay. Can the tonnage be constant all the time? Answer is no. But please, if you have questions, it will take much longer. But assume that for the same tonnage, how the grade varies. That's what this diagram demonstrates. In this particular case, as you can see, if this is my cutoff grade, at that point, the resource model predicts higher than the average of all the simulator model. But it doesn't go beyond the upper limit, the maximum of all the simulations. It doesn't go there. So my personal opinion, my opinion in this model, in this case was, okay, looks like the model that is being used or to be used in the mine planning is optimistic case, but it's not the best. It's not the worst case scenario. If you slide this cutoff grade, that means you're being more selective. You're trying to get more higher grade stuff. Be careful. Your model is not going to actually solve you well. Okay, it's going to go pretty quickly become too optimistic. But if you're trying to get your cost parameters lower and you are in a better price scenario, then you can actually do a mine at a lower cutoff grade. Probably you are in a better place. See, there is a chance that this particular model can also the grade predicted from that model is same as the simulator models, or the mean of the simulator models. What will that means? This can translate into an NPV chart. Okay, just that that's what the previous slide was. If that's a mine plan, the mine plan is the dotted line. Compare that with the average the 350 line. Okay, if you are at the early stage of your mining, probably you are at a kind of slightly optimistic case in this particular example. I've seen all different cases, but this is one particular example. Implications in here, if you knew that this is an upside I have, so that is a potential upside in that particular deposit. Also, there is also a risk factor. So it also cautions you and tells you how much risk in there if you use that particular model, that particular great estimate in the mine planning and go ahead and do the production. Further implications, what happens, what I've seen personally, if you use a good model, you can avoid the situation like this. That means the production target is this and you're producing this line. I don't have to explain much actually here. Okay. I have a whole different opinion about what the production target was. But this particular example, I chose to share that with you because one of the contributing factor was their resource/reserve model, why this fluctuation was. In a bigger picture, you may have seen this diagram before that, if you have ideally, you would like to predict ore as ore, waste as waste material. That means if you compare the two values with the estimated values, you want all the dots line up here. As narrow the ellipse it can be, you don't want this axis to be wider. That means you do not want your blocks to be more blocks to be in this quadrant or that quadrant. These two quadrants are, to me, is equally dangerous. That I shouldn't probably use the word dangerous, but they are kind of contributing to the loss. This quadrant, your ore is misclassified as waste material. Imagine that you have an ore block, you're sending to the waste pile. That's a loss. Similarly, here the waste material, you're trying to send it to the mill, right? It's costing you anyway. A different scenario and different profiles, but to me, this is a loss anyway. You do not want too many blocks in here. Again, what do we need to do? What is the goal? Goal is to narrow this ellipse as much as possible. That means try to predict the waste as waste material as as well as as good and being good actually predicting waste material and the ore material equally. Okay, you do not want too much waste material being misclassified either. So these are operational issues that also comes with, is very much related to the risk and risk profiles associated with any great tonnage estimates. Final thoughts: accept the fact that the uncertainty is there. It's real. Doesn't mean that it's bad. It can be positive when we call it opportunity. It can be negative, which is basically risk factor, right? I don't know how I'm doing time-wise. I think we'll have time for Q&A. It's my last slide. The techniques that I kind of proposed at the end of this presentation is these are non-linear techniques. Okay, they are not very simple. It requires a lot of it requires right kind of software tools, right kind of training, and you need that skill set. These are conditional simulations. It's not just one type, there's a family of simulations. Depending on, you apply the right kind of simulation technique, depending on the geology, depending on the type of data that you have. Selecting the technique is important as the parameters, as important as the database itself. Please avoid shortcuts. This is my personal advice because I have been in those situations. Do not estimate using different parameters. That means just don't create like 100 different Greek estimates, just changing the source ellipses. That's not conditional simulation at all. Okay, and don't use the techniques that that cannot actually model the variabilities in the estimate. That means if you're using inversion square, make sure that you have error factor also set. So you understand how good the estimates are. You understand what the risk factor can be, at least where one variable tell you that, well, there's a potential for risk in this particular estimate that we're going to be either reported or internal. It doesn't matter. It's an estimate of resources for a particular deposit. I think that my strongest advice always, if you need to talk to the people who know how to do the things, if you do not know, anyone, it applies to me or anyone in any forum, I advise always ask for help. If you need that technique, who knows it? Is it applicable? That's probably my last kind of an advice to the end of my slides. This cartoon doesn't need any explanation, and that's my contact information. The floor is yours. You can take questions.
Thank you, Dr. Abani, for your presentation. It was really interesting topic. So now we have about like 14 minutes for questions and answers. So I would like to invite anyone who wants to ask or anyone who has a question to ask.
Well, I guess a very good presentation as always. You know, this concept in resource estimation comes up in economic estimation as well. Probably there are two parallels, and yet there seems to be, when people report a resource estimate or an economic estimate, a lack of what would you call it? The bounds of the estimate, right? Do you think?
Yes.
Do you think that the regulators, which would, you know, depending on where you're at, should think about requiring that, or the professionals who do these things should incorporate those?
I believe Craig is online.
Oh, there you go. There you go. Okay.
Actually, I miss Harry. If you ask me and Harry and few of us, we would say yes, please. But we also know what the problem is going to be. In today, what we're struggling to get a good linear estimate. Okay, I'm saying struggling because many times we get a pretty good estimate. Sometimes we just don't even have the good data. Sometimes we have the data and everything, and the people don't know how to do it. You know, there are all different problems. But here's another good side of it, actually. Many major mining companies, I am seeing them simply because of my association with them. They do it on a regular basis, right? But, you know, they have their own internal things, the way they do it. And some of them also report in that way, okay? They would say, well, our gold you know, amount is this because, and we also used so-and-so technique to validate it, that you don't see from junior mining companies. Over the last 2 years, what I've seen actually in some transactions where I was involved, the financing entities have asked me, or, you know, for people like what I do, to tell them what is the opportunity in it. And depending on which side of the you know,
Yes.
of the transaction is sitting, right? You know, is a buyer or seller or simply a bank, right? So, or another financial entity, you know, they need to know. I guess it is actually, to answer it, to sum up my, you know, my opinion on this, actually, Dr. Corby, is I think this is a good thing to do. It saves the shareholders, you know, investments in any property if they know. And, you know, we always talk about risk. Actually, we are very poor in acknowledging the fact that the techniques actually tell you a lot of opportunities. Most recently, this year, I did a couple of projects. I said, guys, have you not looked at this? So what? Yeah, there's an opportunity for you to just put some more holes. You'll find probably there's potential. You cannot say 100%. There's a potential. Come on. From 0 to, if you have a 50% potential, that's a big jump, man. Right?
Oh, yeah. Yeah, I agree. Thank you.
So thank you for this talk. I'm one of the faculty members here, but I'm not really a mining engineer. I'm a little bit of everything. I'm really interested in, you presented a number of different cases and a number of different estimation methods. And what I'd like to know is, are there people, perhaps there's already been a lot of people talking about different modes of ore genesis, different kinds of ore bodies have recommended approaches for the estimation. Like in some cases, it may be kriging is appropriate, in other cases not. But what I don't see very much when I hear people talk about this is the geologic context for wisdom in making choices.
I get exactly what I know exactly what you're asking, simply because I have been asked many times this type of questions, and your concern is also very valid. Many times we jump into the computer disregarding the geology. I'll simplify the answer. Let's take a coal deposit. I said that I'm not a CP for coal. Okay, I've done probably 5 or 10 deposits throughout my career. That's it. But what I know about coal, you don't want to use even kriging for just estimating the carbon content. You don't want to. You don't need a simulation. It will give you probably some very similar results. However, if you're concerned about the metal content in it, concerned about some other commodities in it, I'll jump to another example. Actually, bismuth in a copper project I was looking at. For copper estimates, good. For bismuth, to simulate, I would like to simulate it. Make sure that your bismuth is properly properly quantified in that particular deposit, and that was porphyry. So personally, myself, if I'm doing an audit or review or full project, I always I'd like to know the type of deposit, style of mineralization, and those kind of things. I always like to read the material that's available in the literature, how this deposit was formed. I will conclude saying that I've been to at least one of my very early time project was in this particular project. The model was done. It was reviewed by third party. The third party said that 10 points. We are the people who did it. I said, yes, the third party's comments are valid because we screwed up. How? The geology was not there. Once you bring the geology, the total grade tonnage curve looks very similar, not a problem. But the model changes, the local estimates change. In this particular case, the first model that was done as if the whole rock is equally mineralized. When I did a little bit of analysis, what I found out that I said that there's a potentially some sets of fractures that are controlling gold mineralization is in Venezuela. I've not been to the site. I'm just looking at the data. And the VP geology says, how did you know that? I said, well, I'm asking the question. Is it the case? I don't know. And I see the structural geology slides after that. And that just makes my day. I say, look, to use the right technique in the right way and apply that is appropriate for that particular deposit, the mathematics behind the computers can actually produce very reliable estimates.
Right, I can see that, but it seems like there's room for more work. And also,
a lot of work.
If you have a knowledge of the orogenesis, you can also introduce a bias in your sampling. So, I mean, it's a very complicated process, but I really seek more geologic context. So thank you.
Always.
Yeah.
Dr. Nelson, you and me know for a few years now, but I'm a practicing geostatistician. I also teach geostatistics to the industry people. But here's something that I start with my course with. Geostatistics without geology is the statistics that doesn't make any sense to me. I'm sorry.
Yep, I agree. Well, I'll yield back to questions from others, including those in the room. Come on, people, let's have some questions.
Or should I throw some questions?
You get extra food if you ask a question.
Is there a question in the room? From the room?
Yes. On the slide you had with the different gold grades that were roughly around 1.7, all the estimates were roughly around that value. Do you ever have irreconcilable like variations, and how would you approach if one number was 1.5 and another was 2.0 versus everything being roughly around 1.7? You know the slide I'm referring to?
Repeat the last thing or last part of your question, please.
How do you reconcile if the data isn't all close? Like all of the grades were within a tight range, but is that always the case?
So you had a slide that you showed with an element, right, with gold, and you started with 1.7, and you showed many estimates or assays that were all around 1.7. So what if some of your assays were showing 1.3 and others 1.7, so that you had a not so central tendency?
Yes, let me address that. First of all, what I was trying to show there, if you use the same assay data, changing the sort, but use the same input data, but changing the sort ellipse, let's say, a geological model, then the estimates of the plot, that may vary. That's what I was showing you there. It's not like the assay values are different. The estimates can be different, okay? The second part of your question is how to reconcile it. Now, if that is true, let's say, when you go into mining, what happens? This is general, I'm generalizing the answer, but different mines do have slightly different approaches. When you have the blast hole data, and if you have a good short-term mine planning department, you take the blast hole data and put in the short-term mine planning, and as a compare that with the block model that you use in the long term. You have long-term, mid-term, like Bingham Canyon, that's long-term, mid-term, and short-term, right? Those departments. So you see if there's any difference in there. And if you are showing the differences, then they're investigating why the differences are. Here is a caveat actually. What is the assumption there? The laboratory that is analyzing the blast hole data has the same or equal quality and reliability as the data that is used in the long-term mine planning. That's the underlying assumption, not often actually spoken, but that's the assumption. If that assumption holds, I'm not saying that it doesn't happen, but I've seen both sides. Then there may be differences in the blast hole data that's going into short-term planning, that the reality, that's what you're going to mine, right? And that you plan based on long-term data, that maybe one of those scenarios, let's say 1.75 grams per ton was actually what you mined, that it comes from blast hole data. And let's say that you predicted 1.65. It's okay. We got a little bit higher grade in this case. Again, assumption is the blast hole data quality is same as or very comparable to the exploration data that was used. Because that's how actually you reconcile. Did I answer your questions? Okay.
So thank you, Dr. Abani, for your presentation, and thank you all for coming here and enjoying like this amazing information. So we would like to see you next week's, where we will have like more speakers and more interesting topics. Thank you very much. Thank you, Dr. Abani, again, and it was our pleasure hosting you. Thank you very much.
Thank you.
Thank you.
I really appreciate you hosting me. Thank you. Appreciate it. Bye-bye.
Thank you. Bye.